Oren Tropp is Sagivtech CTO and has a vast experience in GPU computing and computer vision. Oren brings a unique mixture of expertise in both GPU and CPU optimizations and in state-of-the-art algorithms development in image processing and computer vision. Oren leads Sagivtech research activities on computer vision and is responsible for efficient implementation of conventionally expensive image processing and computer vision applications to GPU systems.
I know this is your last session, and you're probably quite tired, so we're going to have, I guess, 2 breaks between now and 5:45, where your next, where the closing remarks are. This session is about GPU programming. I know you've heard all about HPC. Did you hear about GPUs before? Did you have another session? Not so much? So I'm going to present GPU computing in a very high level, going deeper within the almost 3 hours that I have. Let's see. So who are we? Who I am? I was presented. I'm the CTO of Sagivtech. Sagivtech is actually a company, Israeli company since 2009. So we're about as old as GPU computing. We're about the same age. We have 2 core domains, which are my core domains. Computer vision, image processing, and parallel and GPU computing. More GPU than general parallelism, but we also do parallel computing projects on other platforms. And what we do is 3 things. The last one is what I'm doing here now. It's sort of trainings and courses. We also do them in-house for companies that need GPU training. We do public courses, etc. And we have licensed solutions for both GPU and image processing solutions. So you can buy a licensed product from us to do something on a GPU. We have a few of those, and we also do just outsourcing R&D projects. So many companies, sometimes even within the academy, we have we're part of some European grants for development of fast hyperspectral imaging on the GPU. But usually industrial companies come to us and they say, GPU is not our core domain, you do the GPU part. We'll give you the algorithm, we'll give you a CPU code, you do the GPU part. So this is what we do, and as said, I'm the CTO of Sagivtech. So what we're going to do for the next few hours is first I'm going to show you about 10 slides, just really from a bird's view, presenting the motivation of why go and use a GPU. And after that, we're going to see these 2 presentations, which are actually from NVIDIA. And the first one, we're going to see how to use GPU without knowing anything about the GPU. So how to use it from high-level interfaces, either from just using a library, calling a library function, or programming in a sort of a meta-programming way that you don't really touch the GPU. You don't know there is a GPU underneath. There are a few of those solutions. And then we're going to actually dive into the NVIDIA programming language for the GPU, which is called CUDA. So the reason all this is from NVIDIA is that NVIDIA is currently not just the leader, but almost the only viable options for high-performance computers on GPUs. There are other solutions. I don't know what you've heard about in the previous sessions. You can always use CPUs. Intel has some interesting new platforms that are not yet very well adapted. AMD was competition for a while, but now it's not really considered. It uses OpenCL, if you've heard it. And so NVIDIA is actually pretty much the only GPU viable platform now, these days. Okay, so motivation. So I don't need to, if you're here, I don't need to tell you that modern problems demand vast resources of computation. In other courses, trainings that I did, there's a slide showing that the amount of electricity that some computational efforts demanded, and it's like a small town. Just it's amazing how much computation is needed today. And for a while, serial did a pretty good job, and the serial computation followed Moore's law until about, I don't know, someone maybe remembers better than I do, 15, 20 years ago. The serial computation power followed Moore's law. But then the problem was that there is a time where even though you are willing to put more silicon, more effort into a serial chip, it doesn't get faster. So it's sort of the straight line of the curve. You don't get more efficient as you put more money, more silicon, more power into the chip. And even CPU cores actually today for HPC go into parallel. So you have multi-core CPUs and you have servers with multi-nodes. So the thing is this, once you go into parallelism, why not use more of it? Okay, once you are no longer, if you can do whatever you want to do serially, that's wonderful. Once you go into parallelism, it's harder to program, it's harder to adjust your algorithms to it, but once you do it, why not do more of it? So I have a nice, hopefully nice presentation of it. That's from the GTC a few years back.
Can you increase the
Actually, that's a challenge.
You might do it as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1.
זה שלי לא עובד.
Ladies and gentlemen, Leonardo 2.0. When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs would fly across 7 feet of space and in 80 milliseconds reach its target, hopefully. When it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
And
10, 9, 8,
You can join in.
6, 5, 4, 3, 2, 1. Ladies and gentlemen, science class is now over. Thank you.
Okay, so that's those were the Mythbusters, if you didn't recognize. And that was from the GTC a few years back. And the idea is, well, basically the idea is, as I said, once you are going parallel, it's much more profitable to use many weak cores than a few strong ones. So if you have, if you want to use 100 of the newest cores today, you're not going to get as good performance per watt per dollar as if you'd use 200 weaker cores. So why not use 1,000 really weak cores or 2,000 really weak cores? Even better performance. And the GPU plays on that thing. Problem?
זה לא מקבל את המחשב שם.
מה זאת אומרת את המחשב?
אני כאילו מתחבר למחשב, זה יצא חיבור.
אוקיי. Okay. So, what are GPUs? It stands for Graphics Processing Unit. Everyone has them in their computers because what they do is they render graphics. Historically, they were built in order to draw pixels on your screen from 3D data or 2D data in various ways. And this is a very parallel problem. Okay, if you take a triangle, rotate it, and then draw it with a texture, it is not dependent on another triangle that you rotate and draw on the screen. So historically, it's a very parallel architecture, and for many years it was used only for graphics. It is now already pretty much in the center of HPC. This is no longer a trend. Okay, the market is about 6 years old now, and it's quite mature. So now you have quite a few of the top 500 machines are using GPUs by now. It relies on heavy parallelism. So a CPU would have, how much? A strong CPU, 16 cores? 8, 16, yeah. A strong GPU would have over 1,000. So 1,500, 2,000, 2,000 cores. So we call it massively parallel, okay? And since it's so different, it also requires a completely different coding language, which is called CUDA. It's very different than a computer. This is not just a computer with 16 cores that has been extended to have 2,000 cores. The architecture is completely different, and there is a strong learning curve in order to use this efficiently. It's also more of a low-level thing. Many CPU programmers, they don't know exactly how the CPU works, the cache, the ALUs. They don't know exactly what happens, and that's okay. You can write CPU code like that. You can also write GPU code like that, naive code. But since this is an optimization platform to begin with, usually it doesn't work so well. So you really need to, in order to write efficient GPU code, you really need to be a professional, to know your stuff. We're going to talk about that later. The bottom line is that the raw power of the GPU far exceeds CPU, both in terms of performance per dollar, performance per watt, performance per square meter of space, for everything. And as I said, the downside is that you have to make a special effort to program for it. Okay, so the GPUs, it says here from 6 to 500 times speed boosts. That's obviously a very wide range, so there is a lot of small print to explain that. We're going to talk about it in a moment. You can actually have a supercomputer in a box. There is a box about this big on the widest dimension and this big on the smallest dimensions, and you can fit, I think, 32 cards in there, and you can buy a double card, so each card is actually 2 cards within, and if you do the math, you fill this box with expensive cards, with the most expensive GPUs, and that box would fit in the top 500 computers. So that's it's quite impressive for a box, yeah? GPUs are better at some things than others. So not everything can fit nicely in the GPU. The way that the different the different threads cooperate varies very much from the way they cooperate on the CPU. Actually, the word thread, which is also used on the GPU, is so different from a thread on the CPU that it would have been a good idea to make a different word for it. Okay? So there you go. So how much faster is it, really? So the first answer is a hard question to answer, right? But if you compare raw power means you take the clock speed and multiply it by everything like that. So you're going to get somewhere between X5 and X7. And this is a strong computer. It's not the computer you have at home. It's a computer that costs, I don't know, just below $10,000, I would say. And you take a strong computer and a strong GPU, which costs a few $1,000s as well, and you're going to get a factor of somewhere between X5 and X7 in favor of the GPU, obviously. Okay? But in order to do that, both platforms have to be very, very heavily optimized. This is rarely done. We're going to see an example in the next slide, but this is rarely done. The CPU must use SSE instructions for everything. Okay, no serial code. Everything is with SSE vectors, if that's familiar to you. If not, that's another topic. And you have to use all cores with maximum efficiency. That's also a hard issue. If you have 16 cores, utilizing each one every moment is hard on the CPU as well. So when this is done, then the CPU is about 20% or 15% of the efficiency of a GPU. Okay? When everything is fully optimized. If you are not using SSE instructions, it can very easily go to about 25 times. GPU is faster than the CPU 25 times. SSE is vector instructions. MMX, AVX, there are other words for it. What does it stand for? I forgot. Single. No, it's single instruction, multiple data. Never mind, I don't remember the. But it means you have a vector, let's say 4 floating points vector, 4 floating points values, and you add it to another vector of 4 floating point in a single operation. And the ALUs support that for more than 4 vectors, and that makes it very, very fast. But if you just writing your code float, you don't work with float 4, you work with just a float, that's going to be a fourth of the speed. So in order to fully utilize the CPU, you have to use all cores and everything with SSE instructions. That's actually, in my experience, harder than to write in CUDA. It's harder to write efficient, fully efficient CPU code, in my opinion, than it is to write fully efficient GPU code. This is my experience. Okay, so but it also depends on the application. So there is some small print. If you're going to use only one CPU core, then you can get 100 to 500 performance boosts easily. If you're actually only using a fraction of your CPU. Okay. So this is the GPU edge. So these are practical examples. If you take matrix multiplication, multiplying two matrices, it's a very common operation. It's a very heavy operation. It's optimized on every platform. On the CPU, we used MKL to test it. MKL is the Intel library for linear algebra. On the GPU, we used cuBLAS, which is the NVIDIA library for linear algebra. And the factor there for matrix multiplication is about x5. Okay, so this is the lowest.
Net multiplication or including copying?
No copying. We're going to get to copying later. But for this specific thing, the copying doesn't matter because the computation is so much heavier than the copying because of the complexity of the problem. So this is the lowest you can get, right? Because both CPU and GPU are really heavily utilized. There is no cycle that can be optimized that has not already been optimized. This is from the web, PDE solver. The factor was 16. If you're doing a convolution with OpenCV, if you know I don't know, I'm from computer vision, so I assume everybody is too, but maybe I'm wrong. So if you're using OpenCV, which is a very common library for computer vision, it has many low-level and high-level functions for computer vision. You use the convolution, a 2D filter. The factor is around 100 for a...
It's FFT, right?
That's not an FFT, that's a convolution. Well, you can implement a convolution with an FFT, it doesn't make it the same. This is a linear convolution. Okay? Yes?
Regarding the partial differential equation, which kind of partial?
Actually, I have no idea. This is with open current.
The information is very different between elliptic and
Yes. This is not something that I did. I did this benchmark, I did this benchmark, and I did this benchmark. Not the one that you're asking about. So the factor is x100, and this is not true. It's not actually an x800. This is a wavelet decomposition compared to a MATLAB implementation. So the MATLAB implementation actually was in C with MEX files, etc., but it was no effort was really made to make it highly efficient on the CPU, whereas we made the effort to make it highly efficient on this GPU. So this is why you sometimes see factors like that and even above. Okay? What's the downside? As I said, some algorithms are not GPU friendly. This is not just, doesn't mean only that, it can mean that it's hard to port them to the GPU. It can also mean that it's almost impossible to port them to the GPU. So you're going to get more of an intuition what goes easily in and what doesn't later. It does mean that many industrial companies that want to use the GPU start thinking about it in algorithm design stage. You don't just make your whole algorithm and then port it to the GPU. You think about the GPU compatibility of the algorithm from a very early stage. You need to program in CUDA, a specialized parallel language. It's harder to program in CUDA. I'm one of the earliest adopters of CUDA, and I'm still saying it's not an easy program to write. The tools are more difficult to use. The language itself has to consider thousands of threads working in parallel. It's harder. If you do that, then you get the x5 to x100 or whatever performance boost. Okay. It also sometimes people take it not because it's just faster, but because when you build CPU farms having many computers, you start dealing a lot with communication. And with GPU, because you can put many GPUs in the same box, sometimes the communication between the nodes becomes much easier. You don't actually need to put lines, physical lines between machines, which makes it much harder to build a system. Okay. Questions so far? Just the beginning? Next thing is NVIDIA material.
What stands for
Performance. When I say performance per watt, what is usually measured in GPU computing is gigaflops per watt. Gigaflops, yeah. Okay. Oh, yeah. Okay. So I have one more thing I forgot to tell you. I know most of the sessions that you had like a long talking session and then a hands-on or a training session. We're going to do it a bit differently. This is the last presentation, the last PDF that I'm going to show without writing code. The next one, we're actually going to write the code during, let's say, maybe 2 hours in really small steps. So it's not going to be talking and then writing the code. You're going to write sort of as I speak. I'm going to give you a few minutes to write something, and then we're going to continue from there. It makes it more interactive, and there's less chance of getting stuck, and etc. So, just saying. Okay. Introduction to GPU computing. So that simple drawing actually says quite a lot. See, there is both a GPU and a CPU here. So the GPU doesn't replace the CPU. You add it. The GPU is a coprocessor of the CPU. The CPU is still the running things. It's still the administrator. The GPU performs specific tasks faster and returns the answer to the CPU. It's what's called a coprocessor. And the other thing that you see here visually is the number of cores varies greatly. Okay? If you go online, you go to CUDA zone, for example, you can find these sort of things stating various levels of acceleration using the GPU. As I said before, these numbers are not to be trusted until you read the small print, but they are impressive. Okay, to some level you can rely on them, you can read what other people have done, and you can see if someone has done something that is close to your field. That's useful. So what do? So if this is your application code, you take compute-intensive functions, not all of your code, actually as little of your code as needed. It's better to take just a part of your code and put it to the GPU if that's enough. You take some parts of the code, you put them on the GPU, the rest of your code still runs on the CPU. Okay, that's the programming model. So next presentation is going to be about CUDA and programming directly to the GPU. This one is about how to use the GPU without programming directly to it. The one thing we have is libraries, drop-in accelerations. You have a CPU library, you have a function call, you replace this function call with a GPU function call. Who knows? It's the same API. Who knows the difference? The other thing that you can do is you can use directives. So these are pragmas you put inside your code, and it hints the compiler that these can be done in parallel, and you don't tell the compiler that it's a CPU or a GPU, and your code gets parallel. This obviously sounds really nice. It doesn't work very nice, but it is a viable option. I'm going to talk about it briefly. And the third option is programming languages. Obviously, just programming in CUDA is the fastest thing. There is a layer in between here. You can use something that is somewhere between libraries and programming, a template library. We're going to see that later. So libraries. First thing, let's take a look at libraries. So For many people, libraries are enough. People who do mainly algebra, libraries are enough. You can use an existing library and never know that you are doing it on the GPU. That is an advantage for you, because you can have non-GPU specific people writing all the code. You don't need advice from me. Okay? Ease of use, drop-in, libraries are usually very highly tuned, sometimes by the manufacturer themselves. So there are some libraries that come directly from NVIDIA. High quality, I think I don't need to tell you the advantages anymore. These are some libraries. Linear algebra library. These are two more linear algebra libraries from other vendors. A sparse linear algebra library, image processing primitives that are similar to IPP, more algebra, image processing, and this is an interesting tool called Thrust. We're going to talk about that later. So all these things are available. Most of these are free, not all of them, not in all configurations, but most of these are free. Look them up, see if they help, if any of these are good for you. So the way you use a library is, first of all, you replace the library call of your CPP with a CUDA library call. This is a BLAS call, BLAS call. It adds two vectors with a scaling, okay? And you're going to have to go to your code and replace it with cuBLAS SACSPY, okay? Obviously.
It works only with C or with Fortran?
It works with Fortran as well. There are bindings to other languages, even Python. Okay. So obviously you have to switch the line where you call the function. The next thing you have to do is you have to manage the data locally. We're going to talk about that more later. You have to manage the data on the device. On the host, you do a malloc or a new. On the device, you also have to allocate memory. We're going to talk about that later. So you have to do that explicitly. And you have to rebuild it using the NVIDIA NVCC compiler. Okay?
Sir?
Yeah.
I'm not familiar with this. When you change from SACSPY to cuBLAS SACSPY,
Yes.
the arguments are the same? It's a very trivial question.
Yes. The arguments are the same more than 90% of the time. I don't know if it's 92 or 99. Okay, so this is an example. We're going to see how it looks with cuBLAS. This is the original code, okay? This is a CPU code. This is the same name but with cuBLAS in the beginning, so it's now an NVIDIA function. And notice that the name of the variables have changed. It was... no, they didn't change it here. Okay, then. But these are device buffers. These buffers no longer reside on the CPU. They are on the GPU. You have to init cuBLAS in the beginning. You have to shut it down when you finish. Those are initialization and termination functions. This is the allocation, cuBLAS alloc. You actually have to manually allocate the data that you're going to use on the device. And then in the end, you have to free it.
What's the overhead for doing that?
For allocation?
For initialization?
At initialization, you do at program startup once. It's very low.
And the allocation?
The allocation takes time. It also takes time on the CPU.
Yeah, but does it take milliseconds, microseconds?
I'd say it differs. If you want to really optimize your applications, usually you don't make dynamic allocations. You allocate at startup and you use the same buffers over and over.
Oh, so it's memory buffer on the GPU's memory?
It's on the GPU's memory. Yeah. We're going to talk about GPU and CPU memory later. It will be clearer. So obviously if there is GPU and CPU memory, you have to copy between them. So you allocate GPU memory and then you copy from the CPU to the GPU. And then when you finish, you copy the result back. Okay, it's like copying it to another machine, performing something there, and then copying back your result. You have to explicitly do that it doesn't get done automatically, although there is a way to do it automatically. It's less efficient. Okay? This is obviously very naive code. I'm not saying this is efficient. If you do this operation with a GPU, you're doing something wrong, because it's very fast on the CPU, and just transferring it, the data copy to the GPU is going to be longer than the time you save. So this is just an example. So you read the data back to the CPU, and it's done. Obviously, you don't have to copy it right back. I'm saying something that might be obvious, but I want to state it. If you have iterations, linear algebra iterations, 300 iterations, you don't need to copy it back to the CPU all the time. You can perform all 300 iterations on the GPU, copy back just the final result. Okay, so this is for you. This is just for you to have a link to go and check it out. And we are down to directives. So how many of you know OpenMP, for example? You learned it here, right? Okay. So the idea of OpenACC was to be similar to OpenMP in the sense that it will be accepted very generally, and many different vendors would have compilers compiling OpenACC code to CPU, GPU, and other platforms. It didn't work quite that well. And OpenACC is sort of stuck in the middle. The idea is that you can write code, as you would in C, give the compiler a few hints that some parts of the code are parallel, and it will be deployed on whatever platform. It's a very nice idea. It met with some problems, and right now I would not recommend it for most users. It is very useful for some people who have legacy code. They don't want to change the code. They just want to put a few programmers in and get some acceleration. It is useful for that because you don't change the code. You only add programmers. It's not so useful really HPC right now. You're going to get some slides later that show that it is. It's not really happening right now. So what's happening now is that I think this is Fortran. You're writing loops, and you're doing something within the loop, and all you do is you tell the compiler that these loops perform operations that are independent. The pragmas tell the compiler that your operations are not dependent on one another, so it can actually do different iterations of the loop separately by different processors. That's the idea.
So why inventing a new set of directives? I mean, the compiler could take an OpenMP code and see, oh, this is an OpenMP code, and already someone put this OpenMP do parallel directive in front of it, so of course those iterations are independent.
Yeah.
Why inventing a new set?
Because the hints you need to give a compiler in order to do things parallel in a GPU way are very different. You need more hints than you would need on a CPU.
No, but at the end you are saying the same. You tell the compiler, okay, go and parallelize this code, however which method you choose, but what I'm telling you that those iterations are independent.
Yes.
That's the whole information.
No. You can tell it more than that. I've given you the short version. The more you tell the compiler, the more hints you give it, it's going to do a better job. If you just give it that one hint, for many kernels, for many functions, it will not give you a really good acceleration. You're going to have to tell it more, and this more does not exist in OpenMP. Okay? So this is actually not my expertise. These are some optimistic quotes from the very first days of OpenACC, which was, I think, done by PGI. It didn't live up to the expectation right now. Maybe it will pick up. I don't know. Don't believe me. Check it out for yourself. So this is an example. You do a copy, an OpenACC copy, because you have different devices. This is not generally the host. You have to copy manually from the device to the host. More on that later. And then there is a parallel loop. And you do something within the loop that is parallel. The things that you would put inside an OpenACC loop are not generally the things that you would put in an OpenMP loop. Inside an OpenMP loop, usually you put high-level functions that do quite a lot of work. Inside an OpenACC loop, you would normally put something extremely simple, like adding two floating point values and writing them. Very simple things you put inside. So it's a different thing. And this is the PGI Fortran compiler with NVIDIA, and hopefully your code gets accelerated. This is another example. I'm not going to get into that. This is not really my expertise, and right now it's very hard to do that because the company that did that ran into some problems, and I don't know, last time I tried to download it, I couldn't. So, okay, so that's the optimistic version. Oh, I'm not running full screen. Okay. That's the optimistic versions. There were some people apparently who say they managed to have their application run 5 times faster in just 8 hours of work. Well, okay. That's another link you can follow. And we are down to programming languages. So, programming languages, as I said, the lowest level one is CUDA. But you can also program to the GPU through other interfaces. OpenACC is the Pragma language we've just seen. Thrust, we're going to talk about a bit, is a C++ functor function. You can also access it from Python. You have, in MATLAB, you can have Pragmas in MATLAB telling you that some for loops can run in parallel, etc. There's quite a lot of ecosystem. As I said, this field is still sort of in the exponential growth phase. So you get more and more tools still coming up. Okay, so this is your first sort of view of the difference between serial and parallel code. And it's a very simplistic example. That's why it's simple. It's going to get a bit more complicated later. We're going to do the vector addition with the scaling that we talked about before. This is the SAXPY operation. So you take in 2 vectors, x and y, and you take a floating point constant, and you multiply x by the constant and add y. You do that not just for one element, but for a whole vector, and that's it. You multiply by a scale and add another vector. That's what it does. And this is the serial code. You make a loop, and you iterate on all the elements of the vector, and you do the same operation for them. This is how it would look in C. Very interestingly, this operation in C that says you do that thing, do this simple operation, but do it 1,000,000 times, not just once, do it 1,000,000 times, also tells you the order in which you are going to do it. You're going to do it for the first element first, on the second element second, etc. In a parallel execution, what you would say is, I have 1,000,000 of these, perform this operation 1,000,000 times on the different elements, and return to me when you are done. There is no order. And this is what actually happens here, sort of. What you see here, there is no loop. The loop is gone. Instead of a loop, what you have is you take the index of the element you want to work from some magic variables. These are magic variables. And then you operate on the data. And there is a really strange thing, checking whether I is smaller than the number of variables, which they put here now. Really strange. But this is CUDA code, and it actually works. This code is operational. It works. And what happens is, you sort of do this. You tell the function, your function, that what the basic operation you are doing is this. But then you have to tell it on which element to do it. And which element to do it comes from this first magic line that we're going to talk about later. And these magic variables, if you have hardware with 2,000 cores, these magic variables are going to be different for each core. And that's how each core will operate on different index. So this is a very first introduction. So you will actually write code doing that later. So this will become clear. Okay?
So what is block I need?
But later.
Sorry, but it is very crucial that there is no data dependencies. I mean, the indices I are never depend on each other.
Well, the whole concept of this is that you are going to perform this simple operation.
It can be done even in random I.
Yeah, it can be done in random I, and the different the different instantiations of this line are independent of each other. Okay? Oh, and this is the way you would call it from, this is the usual way to call it. This is a C way to call it, and this is a CUDA way to call it. So you have arguments here, but you also have that weird thing here. See? Those triangles here, that's a CUDA syntax. More on that later.
But this is inside of the main program?
Okay, good question. This will run inside the GPU, and it's written in CUDA. This line exists on the CPU code. I said before, if you remember, that the CPU remains the administrator. It tells the GPU what to do. So this is the line that says, in which the CPU says, GPU, go do this. Okay?
Now what distinct the architecture that you are running? What distinct the first code from the second code?
Later. That's just the preview. Okay, we're going to get to that later.
The device?
Okay, so you could also write C++ CUDA. This is C CUDA. This is basically C. And CUDA now supports many C++ functions. So you can have templates in CUDA. And you can have functors and functions in CUDA. And you can have operator overloading. And you can do new and delete from the GPU code. You can allocate and deallocate memory, etc., etc. It's becoming more and more rich. So for example, just if you take this code, the functor here is plus, right? Or let's say even the functor here, if you could do any operations on two variables, x and y, and the code would be almost the same, except here you would have to do something slightly different. That's called the functor. So you can actually write a kernel like this. This is called the kernel, and pass it a different functor, and it will perform any operations you would want between the vectors x and y in this fashion. I'm not saying this now to really teach you how to do it, just that the CUDA language is already quite rich, and it supports functors and things you would normally do with std vectors, and not with low-level stuff. So the easiest way to do CUDA without CUDA on the GPU is with Thrust. Thrust is a C++ template library. You don't need to know CUDA in order to use it. It's very similar to std vector with most of the concepts, even some of the syntax. You can see here things like begin, end, copy, being given iterators. It's very efficient. Even though it's a rather high-level interface, it's extremely efficient. So you can safely write code with Thrust and not worry that you can get an x10 factor if you write it in CUDA. And it's quite comfortable to use. I use it in any projects that I can. Although I know good CUDA, I would use Thrust just in order to save time. Let's have a look at that code. Namespace Thrust, you define the host vector of integers. It's like an std vectors. You generate element from beginning to end with an operator rand. This is a functor. You can copy with the equal sign. You can copy from a device vector to a host vector. This is a device vector. This means it sits on the GPU. This is a sort, so you can sort values. With one line of code, you can do sorting on the GPU. Okay? So what thrust is really is this. You have data containers, host vector, device vector, data containers, copy operations between them, iterators. So you can do some fun stuff with iterators. I'm not going to go into that now. If you know to do funny stuff with iterators on the CPU, like zip iterators, tuples, if that rings a bell, you can do that on the GPU. It's actually, I think, the most advanced iterator environment. And you have algorithms. That's the beautiful part. You have algorithms that are already implemented on the GPU, and they are implemented in a templated way. So you can not just sort values of integers, you can sort really complex structures having many different fields inside or whatever, and you can fuse between elements and sort them in the same operation, because thrust supports something that is called a zip iterator that enables you to sort of put data together and then operate on it. This is if you know C++ very well, this is a really nice tool to use, and it's really efficient.
And it has a CPU version as well?
It has yeah, good question. Good question. It's not just a simulation. Thrust is open source, and it has a TBB backend. Threading, I always forget the acronym. TBB?
Threading building blocks.
Yeah, threading building blocks, thank you. Threading building blocks infrastructure to do it. So you can write a host vector, do a sort on a host vector, and it's not a naive sort, it's a TBB sort. But actually, let's say the truth, since NVIDIA did that, they didn't go into that much trouble to make it extremely efficient on the CPU.
Yeah, but suppose you don't have a GPU yet, but you want to develop the code, so you first do it on the CPU and then just code it.
Yeah, you can do that.
You link with different libraries.
Yeah, you have to use well, thrust is because it's templated, it's an H file. You only include it, and you only need to have NVCC in your path in order to compile it. Okay.
You need to select the correct version, the CPU version, or the.
If it's a device vector, it's going to get done on the GPU. If it's a host vector, it's going to get done on the CPU. Okay. By the way, this is very interesting what you said about not having a card yet. I hear it a lot from the academy. A cheap NVIDIA card costs $50. So I know sometimes in the academy it's as easy to get $50 budget than it is to get 50,000, 50 million. Sometimes it's easier to get 50 million. Yeah. Okay, from my side, it's funny, you know, because you can just go get a card for $50 and start working. You know, I have one on my laptop. You know, so.
I mean, the 600 series you can get now if you buy a standard workstation. You take the but they have a big screen and need a graphics card, and you get a 600
Yeah,
series.
it's just a graphics card you buy for your desktop computer. It's nothing special. And US architecture, no problem. Okay, so. Anyway, so you also get my moods, so you got the idea that I don't like OpenACC, I do like thrust. So.
The thrust, does thrust play nicely with
I never did thrust with Fortran, but I guess it really works fine because it works with Python, so I guess they would do.
So you have to go with thrust, Python, Fortran, and then Fortran, Python.
No, I think they have a Fortran version. They usually do. Okay, so you have CUDA Fortran. I've actually never done CUDA Fortran directly. I have written kernels in CUDA C, and I linked them with Fortran. But you can write directly in Fortran. And there are other programming languages that through which you can access the GPU. From Python, you can access libraries. For example, kublas you can access from Python. But you can also access thrust, the templated library. You can also do that from Python. You have bindings from C#.NET, from MATLAB, from Mathematica. whether through libraries or through sort of these parallel for loops.
GPU.NET is in the .NET framework? It's already there?
There is, I think it's just a way to say that that's the binding that from .NET environment to the GPU. Okay, so this is again the the links you're supposed to be left with. CUDA, Thrust, Fortran, Python, Mathematica, MATLAB, and .NET environments. This is where you get started with your favorite environment. Okay.
Can you say a couple of words about MATLAB with CUDA, or MATLAB with GPU in general?
Yeah, I will. It's actually a good time to say it because we're going to go into CUDA in a moment. And we're going to have coffee before, don't worry. So I'm just going to say a word about this. I'm not going to talk about this now because you can read it later. We already discussed all these ways. It's 6 ways to write that scale vector ed thing that we talked about before using CUDA, Thrust, Python, Fortran, all the options, kublas, etc. To your question, first of all, the general answer is that most ways to use the GPU, which are not low level, are not as efficient. Except library calls. Because if you call a library and the library has been written very efficiently, then you have full efficiency, right? When you start from MATLAB, the first thing that occurs is that data is transferred from MATLAB to the GPU. And if you're not working very efficiently, you also pay for transferring the data from MATLAB to the CPP. You have to do that properly as well. And then you transfer it to the GPU, you do something, and then you get it back. It's only worthwhile doing it if you have more than a little data. So we've written many functions that have a MATLAB API, and if you send an image that is, if you send Lena, 256 by 256 image, then no acceleration. It's slower than doing it in MATLAB. If you send either a huge picture, let's say 4K by 4K, or you send a stack of small pictures, don't just do a histogram on this small picture. Do a histogram separately for these 100 pictures. Give it 100 pictures at the same time. It's called batching. Then the copying becomes less important, and you will get acceleration. The way you would get acceleration from MATLAB is either by library calls or by using there is like it's like the Pragma language, a Parralel 4.
Par 4.
Yeah, there are 2 implementations. One is from MATLAB and one is from another vendor, Jacket or something.
Jacket is not anymore. It's not supported.
But it was a third-party thing.
Separated. It's accelerated, right?
I have no idea. What I dealt with that like half a year ago, and there were 2 solutions, one from MATLAB itself and one from an outside vendor, and one of them is gone, you say?
No, the vendor not, but they are not working with MATLAB.
Okay. Okay.
No, the vendor is the other ones where you show the matrix library, rapid fire.
Rapid fire is theirs? Okay. So the thing is this. Everybody demonstrates matrix multiplication and shows that it works really well. And that's a really nice thing. I would also show it. Matrix multiplication has distinct advantages as an example. It's very computationally intensive, but it's very simple operations that any platform can do. It's so computationally and expensive that the data copying is negligible. If you take 2 matrices that are 1,000 by 1,000 and copy them to the GPU, it takes a few milliseconds, but it takes a second to multiply them. Okay? So transfer times are negligible. It's very easy to parallelize. It's the ideal example. And if you've seen an example of them doing it in MATLAB and parallelizing it on the GPU or something, or in OpenACC, then yeah, that works. I don't think that generally you're going to get really good accelerations working from MATLAB on the GPU, except with libraries. If you use the library function, why not? That would do.
What is the break-even size that the GPU, the GMM, for example, will be faster than the CPU?
That depends on bus speed, which differs, GPU strength, CPU strength, the port in which you transfer the data. That's a specific question.
But if the matrix will be too small, let's say 10 by 10.
Do it on the CPU. Unless you have 10,000 matrices that are 10 by 10. If you have 10,000 multiplications of 10 by 10 matrices, copy all the data in the same times to the GPU, and there is an interface for multiplying 10,000 matrices at the same time, and this will be very fast. Okay? So again, for intuition, okay, check the tools, check it, because as I said, matrix multiplication can be done with pragmas. So maybe your code is very simple and it can be done with pragmas, check it, but otherwise you'd get good performance either using libraries or writing low-level code. The middle, not so good.